Hello, and I'd like to welcome you to this roundtable webinar today, Quality Inspection and Measurement in Aerospace. My name is Ben Sampson. I'm editor of Aerospace Testing International magazine and will be hosting this webinar today. The roundtable webinar is going to focus on the vital aspects of inspection and measurement in aerospace and aviation. It aims to explore the crucial role that quality inspection and maintenance technologies play in ensuring the continued reliability and efficiency of aircraft and their systems. So I'm not going to be the one talking about this. I'm going to be the one posing the odd questions to the panel of experts that you can see in front of you. I'll now just introduce those experts, going from, well, on my screen, left to right. So joining us is Jean-Sébastien Blais. Hello, Jean.
Hello, how are you?
Very well, thank you. Good, yeah. So Jean is a global expert in enterprise solution deployment for InnovMetric. He helps manufacturers digitally connect their 3D measurement data to their product engineering and manufacturing processes through InnovMetric Software, which is called Polyworks. He has 20 years of experience doing this, integrating their software solutions with measurement devices within quality control processes. Previous to working for InnovMetric, Jean-Sébastien worked at Bombardier as an aircraft systems engineer. Jean, do you want to give us a bit more background or tell us a little bit more about the product?
Yes, of course. So for those who are not familiar with the name InnovMetric, we're an international company that provides software solution for acquisition and processing of 3D measurement data, and very recently, the sharing of its result across an organization. And like you mentioned, this software is called Polyworks, has different modules to it, and they are used for specific purposes, of course. And like you mentioned, my role is most likely to help companies integrate the Polyworks enterprise solution to their manufacturing processes.
Great, thanks for that, Jean. So I'd like to introduce now Rob Hewison, who is Technical Manager for Composites at the University of Sheffield's Advanced Manufacturing Research Centre. So Rob has 30 years of experience in the composite industry, has worked on manufacturing, tooling and design projects in sectors from Formula One, racing cars to defence and space, with metrology and NDT being critical throughout his career. He joined the University of Sheffield's AMRC in 2012, having been associated with its Composites Centre since its inception in 2006. Recent projects include Project Compass, Composites at Speed and Scale, which aims to boost composites R&D for aerospace. Prior to this, Rob was 20 years working for Lola Composites as quality and then technical manager, with a focus on the liaison between design and manufacturing, producing race cars for all series, including Le Mans and F1. That sounds fun, Rob, and thanks for joining us today. What are you working on at the moment? What's your focus at Sheffield?
So for those who don't know, the AMRC is part of a wider network called the High Value Manufacturing Catapult in the UK. And around the catapult, we have a number of centres sort of focusing on various areas. The AMRC are a little bit different because we have expertise in a number of areas, including automation, composites, machining, castings, and various other technologies. So we work on a lot. My focus is obviously in the composites area, and as your intro said, Ben, we're just in the process of planning to build a very large, fully automated aerospace capable manufacturing line to try and tackle the rate challenges for future aircraft.
Great, thanks Rob, and thanks for that bit of background on what's going on at the moment. So I'd like to introduce next Dr. Erik Novak. Dr. Erik Novak is Vice President and General Manager of 4D Technology, which is a subsidiary of Onto Innovation. So Erik has been Vice President and General Manager since 2013, but has been developing instrumentation for more than 24 years in applications such as semiconductors, optics, aerospace, automotive, photovoltaics, and medical devices. He's received 7 international product awards, holds over a dozen patents, and has more than 60 publications and book chapters related to surface measurement and industrial process control. Hello, Erik. You're dialing in from where? Tell me.
From Tucson, Arizona.
Great. Thank you so much for joining us. Can you give us a little bit more background on 4D technology and on what you guys do?
Yeah, so 4D technology really was founded originally for precision testing of optics and had developed a way of testing optics that was immune to vibration down to the nanoscale level. So if you're familiar with the James Webb Space Telescope that just went up, we had sold more than 24 instruments into that program, measuring everything from the mirrors and lenses to the carbon fiber scaffold that went into it. And we got into aerospace probably about, started maybe 8 or 9 years ago. We were approached by GE Research, and they had the need of getting quantified metrology on the shop floor, because they were finding they were rejecting and reworking 40% of good components because the inspectors just didn't know whether things passed or failed. And so they wanted to replace eyeballs and fingernails with quantification, and we developed the Inspect product line to help them do that. And then that's been growing and expanding into different additions like edge break and roundness and corrosion measurements and everything ever since.
Okay, great. Thanks, Erik, for that little bit of background. And finally, I'd like to introduce Tom O'Hare, who is a technical fellow at Spirit Aerosystems and has managed materials science, non-destructive evaluation programs, and the industrialization of advanced diagnostic inspection platforms for multiple component types. During his more than 38-year engagement in NDT, measurement, materials science, fatigue analysis, damage tolerance, and fracture mechanics, he's been involved with many development, in-service, and manufacturing programs, and has had significant experience in novel metallic, composites, polymers, and ceramics materials. Thanks for joining us, Tom. Quite a few mouthful of stuff that you're involved with there. Can you tell me what does a technical fellow do exactly at Spirit?
Technical fellow is seen as a subject matter expert at quite a high level, and is responsible for trying to help and direct the organisation to make appropriate decisions on maybe technical problems or issues that we may see, or maybe look at maybe production or manufacturing problems, or even in-service problems that are helping out our customer to understand where we have process issues, etc. So it's a broad remit. My remit is within materials science and materials process and test engineering, which covers some of the inspection, metrology, and NDI processes that we use.
Okay, thank you for the more elaborate answer than your answer before was very succinct, wasn't it, when I answered, but probably not repeatable here. So thank you for not responding in that way. So I'll just do a little bit of housekeeping before we move on to the questions. The structure of this webinar, it's going to last for an hour. We're gonna talk amongst ourselves, hopefully for around 30 minutes, 20 to 30 minutes. But what I'd really like everyone to do, if you're watching now, is submit your own questions via the Q&A box that you should see on the right-hand side of your screen. I really can't urge you too much to do this. What often happens is people will wait to the very last minute to submit their questions. Please do submit them as they occur to you. I won't read them out straight away, but they will be published for everyone to see eventually for the panel to answer. So whatever you want to ask our panel of experts, and we've got some great experts here, this is your opportunity to. Finally, there is also a handouts tab on that right-hand side of the page for you to download some information about the companies that have very kindly sponsored this webinar and made it possible. Those sponsors are InnovMetric and 4D Technology. So please do avail yourself of that download. So that's it, really. We're now launching into this. I mean, we've had some conversations offline about what we're going to talk about. There was some very exciting things going on at the moment in this space. So I'm going to kick off with a question here for Erik. Let me just pull it up. Sorry, Erik. About 3D measurement. So, Erik, to you, where does 3D measurement fit into the overall development manufacturing inspection processes in aerospace? If you could answer that, please.
Yeah, so it's becoming, more and more critical, particularly as, component tolerances tighten, right? So it used to be, the calibrated fingernail was good enough for assessing depth or some visual comparators, but really as companies have wanted to optimize efficiencies for fuel efficiency, as they're worried about, global warming and things like that, as they look at longevity of parts, as aircraft go into more difficult environments, they've really been pushing the boundaries of capabilities, and that's really meant they need to quantify everything from edges to contact points and things like that, and being able to do rapid CAD comparison using programs like Polyworks and do advanced lifing models and things like that have really brought 3D into the realm of being a necessary technology rather than an interesting addition to the portfolio.
We can't hear you.
We can't hear you, Ben.
Sorry, I was being a good participant and muting my mic while I wasn't speaking. I'll just drop that there. Does anyone else want to come in there about where 3D measurement is being used within that development process of manufacturing? And that was just good.
I'd say it's also all about efficiency. When you have parts that are immediately fitting well together in a large assembly as complex as an aircraft, for example, you're gaining a lot of efficiency in terms of avoiding certain problems. Also, there's the aspect of international manufacturing, where now you would have a fuselage that is manufactured in a plant that would be in Europe and being assembled on an aircraft in North America. So basically, if this situation occurs, if there are ways of performing an inspection and using 3D measurement data to predict how well an assembly will match together before the two parts are actually, or components are put together physically in the same plant, you have a great advantage, and you can have a head start over competitors if they don't use those technologies. So there are tons of examples like that where it proves that you're getting a better efficiency at your manufacturing process by using 3D measurement data.
Okay, thanks, John. Go ahead, Rob. Sorry.
No, sorry, just to add to that, I mean, one of the biggest challenges is making that data available as quickly as possible as well, to enable us to react to the data and to enable sort of downstream processes to actually accept parts from the 3D data. So there's a lot of work to do in updating all the systems that drive that, especially with the drive for higher rates in future aerospace. So the real big challenge, I think, is being able to use that data fast enough to make it useful almost in real time, or as close to real time as it can be.
Yeah, that's great. Sorry, that's a great point, Rob. That's actually one of the reasons, or another reason, that we were asked to move metrology from the lab to the shop floor, and now getting more into automation, is you can't afford to produce a bad part, send it off, and get an answer next week or 2 weeks from now. You really, with the requirements on manufacturers these days, you want that feedback within minutes rather than days or weeks.
Yeah. The composite manufacturing process is very complex, and you can have a lot of deviation from the models that, from a manufacturing perspective. And if you know how far you're out or what's happening, or you can see a process drift, and you can do it on the shop floor as a part of the manufacturing process, you can actually make changes, not quite on the fly, but you understand where you're having issues and what you can do, or you can predict to your final line assembly, wherever it may be in the world, what you're producing as it leaves your factory, so that it can be adapted or changed as it's going to your final assembly areas.
You know, it's very interesting, this concept of a digital passport and the data that follows the part into the downstream processes, and the metrology data in particular has a significant effect on those downstream processes. And from what we're seeing, looking at very large scale, high speed processes, the benefit of some of these processes is that the downstream assembly or follow-on processes can be reduced to a minimum. But understanding all of that and then analyzing the data afterwards is the key, and then building that knowledge base, if you like, and using tools such as AI, I guess these days, to assess that data is really key to being able to meet the demands of really high rates in the next sort of phase of aircraft production over the next 10 years, I guess, is the best description.
Yeah.
So we've moved fairly quickly into talking about data, of course, and it's often seen as a resource now, rather than and testing a resource that testing and inspection produces as well. Jean, I know you've got some points around this that you'd like to discuss.
Yes,
Yeah, so please go ahead.
I would say that it's important to do metrology and to have 3D measurement data to provide results, and to understand, like Tom mentioned, you need to understand where you're at with your part. But in reality, one of the reasons why we jumped into discussing about data so rapidly is because in the end, all the data is useless if engineers can't get their hands on it. And it's important, it is as important to capture that data, but also to make it available so we can have almost real-time feedback over what's going on with that part. And basically getting access to that 3D measurement data is also key. So it's not only a question of, do you have 3D measurement data, but it's also who can access it and how fast can you actually make a decision by looking at that 3D measurement data. So this is also a very important component of 3D measurement data.
So how is that achieved? I mean, or how is it best achieved, to the sharing of that data? I mean, I could throw some buzzwords in, digital twin, digital thread, but ultimately, it's you guys that know about this stuff. I mean, what's the most effective way of getting at and working and using that data in the best possible way in a manufacturing environment?
Yes, currently the solution that InnovMetric came up with is the use of a product that we call Polyworks Data Loop, which in layman's terms is basically a database where everything you measure gets uploaded to a database, whether on premises or on a cloud solution, depending on what the company wants to work with. But basically, this is a secure environment, which is very much analog to what people know as PLM system or part life cycle systems that they have for CAD models for years. In fact, back in the 1990s, there were such systems around, and database have been used for a long time. But when we're talking about 3D measurement data and the virtual twin, as you mentioned, when we have a digital version of a part with all its irregularities or defect that is stored in this centralized data management system that's accessible for an organization no matter where they are on the planet. This gives a great advantage because you can actually immediately get access to that data and conduct maybe root cause analysis, and engineers can get their hand on it. So it's not just staying on a computer on the shop floor. This is something that is readily available immediately after the measurements have been gathered on the shop floor.
There is a small issue in regard to data management, is that you've got a number of different measurement techniques and tools and software platforms. And even in the one company, even in our own company, we have several different versions of measurement tools or metrology tools. So there's no common platform for acquiring the data or even reading the data. Sometimes you have to do either a transfer, or you have to even dump it into Excel spreadsheets or something like that to try and manage the data. So I think it's important, we have historical data that was captured with old measurement systems, and we struggle sometimes to pull that back again, or to actually use it as part of our modern manufacturing process.
Is this a relatively recent problem, Tom, or how?
It's within the last 20 years we've managed to be very capable in our measurement capability, and we've increased the amount of data. How well we use it sometimes is subject to question. Do we turn it into useful data? But yeah, the different measurement systems. I'm going back from even Renishaw probing to PCDMAS to Polyworks. We have quite a number, and legacy with quite a number of different systems, and they don't all talk to each other or cannot be read. And we have different platforms, different arenas, and different countries that we'll have different processes in.
It also.
Sorry, go ahead.
Sorry, guys. I was just going to say that the integrity of that data and understanding how it's been captured, and to Tom's point, being able to align it with data from other systems or from other plants, for example. Jean, you spoke about, a worldwide manufacturing, and aligning all of that using all the same, exactly the same equipment is a bit of a utopia that's not going to exist. But It is really important that we understand the integrity of that data, especially as you combine all of these potential inputs. As a research organization, and we're looking at things, from across a number of different organizations, just trying to get data that can be almost overlaid with the equivalent data from somewhere else is often very, very difficult. And to Tom's point as well, it's often in your own organization quite difficult to do that, depending on, the age of the data or who was doing it or which site you were working on.
Yep.
And so there's a huge amount of work needed, I think, to align all of that to enable us to really use what is becoming a currency. I mean,
Yes.
Data in itself is becoming a currency in its own, isn't it? In our world, I think.
This is one reason when we're talking about deploying our enterprise solution, one of the very important aspects is the universal platform. And what we mean by this is the fact that, yes, there are equipments that can be used directly inside Polyworks to gather data. But what about all these other systems? There may be very good reasons for continuing to use another data acquisition software to drive, let's say, an old CMM or something that would not be directly compatible with our software platform. Well, in those cases, we have an open architecture which allows us to bring the 3D data from those other equipments either through one of their native exports or through a translation mechanic that would adapt their output files to something that we can read. So this is part of the universal platform that Polyworks is and that InnovMetric promotes. And of course, this can be seen within a single plant, but can be seen also across organization when you think about their suppliers. So like you said, it's a utopia to think that a single software can replace all the different acquisition systems that are out there. But the reality is, once you want to deal with central metrology data in a data management system, you have to bring it in a single location. Like in an organization, you wouldn't think about having different CAD platforms where all these different components would be stored in different databases for a single vehicle or a single aircraft that's being manufactured. So it's important to start seeing 3D metrology data the same way. You have to have a central 3D metrology database.
Okay, great. I'd just like to move the discussion on slightly. Data's great, but of course, getting information and actioning on that information is another thing. In situ process inspection. Are people implementing it? What are the advantages? Why would they implement it? What's going on there? Does someone want to start there? Take that question.
Yeah, I mean, from our standpoint, it really is, it's about efficiency and really enabling the operators of the production equipment or to control the process in near real time if they can, right? So again, as you look into industry, measurement labs typically do have pretty significant backlogs. And a lot of times, as I mentioned earlier, it could be a week or two before things get through the queue. And at that point, especially in aviation where component costs are so high, and right now labor utilization is, everyone needs more people. Getting efficiencies in the process is critical, right? Reducing turnaround time, making sure things are going out the door good. And so the closer you can move metrology to the area where it can be used, the more efficient your operation is. And that does come with challenges, right? Because the person on the shop floor is typically not as sophisticated as someone in the metrology lab, right? So you have ease of use concerns. You have to give them real-time feedback in the quality of the data. You have to, have easy pass-fail criteria and things like that. And also, not allow the operator to, tweak things and actually, pass things that shouldn't pass. Not that that's ever been a real problem in aviation. It's usually the reverse. If there's any uncertainty, inspectors always will fail apart in aviation. But that leads to an enormous amount of scrap and rework that might not otherwise have to happen.
I think there's a very interesting point as well, Ben. You ask about why in-process inspection is increasing, and as tack times come down and as the need to produce things more quickly becomes apparent, you need to very quickly assess the suitability of a part for passing on to the next process and do that in a much more integrated way. And there's very good examples in the composites industry of laying up plies on very large aerospace parts in 45 minutes, and then the system basically waiting whilst there's an hour and a half of inspection before it's passed to the next step. Now, in some ways, you halve the inspection time, you've doubled your throughput. And so the benefits of having in process are twofold. There's the need to keep non-conforming parts or parts that could non-conform out of the system. And more importantly, if you're going to find a non-conforming part, you want to find it as soon as possible, so you're not then costing yourself significant time and money on parts that in the end aren't going to be used. So to my mind, looking at it from a manufacturing perspective, they're the two challenges in particular that need for that immediate in-process inspection has got to resolve, I think. I don't know. I guess Tom's got some pretty similar views on that. I don't know.
Yeah, we have to be more positive about how we start our measurement process, and that even comes, as far as I'm concerned, from you first ply down on a tool. That's when you should be really starting your measurement process, so that you know that how you're putting on your raw product before you go to a cure cycle or an infusion cycle, that you're doing that appropriately. You're not missing plies. There's nothing left in the component that shouldn't be there. You know exactly where you're going. You know your tools and profile, because you really technically you should measure your tools, make sure it's okay. So that the basics from the birth of a product, and then as you bring it through the autoclave process or out of autoclave process or whatever way you cure, there should be measurement points that are swift, rapid, using line of sight, using optics, using lasers. You go into your machine tool to do whatever appropriate machining. You can use your machine tool as part of your metrology process as well, because it needs to know where everything is in space and time. It needs to be accurate in its machining. It can give you a data output to how close it is to the model as you machine. And then you go into the next process, and in some cases we would use NDT as one of the process checks for the integrity of the component, but we also use it for thickness measurements to make sure the ply stack thickness is appropriate, etc., etc. And then you can go from there into a dedicated metrology machine if you wish to, or if you have to, or if there's some key characteristics that have been flagged up earlier in those measurement processes, then that's when you have to do a full metrology evaluation of the component. So it has to be from cradle to grave, or from cradle to out the door.
Yeah.
Okay. All right. Thanks. I will just put in this question from the audience here. I'm going to attempt to pronounce its name. Gangad Soraya Prasemp. I do apologise for absolutely mullering your name there. He's asking, is there a possibility in future where a metrology engineer asks Polyworks software to input CAD, align with a scan, and create an FAI report, and it delivers it in a few minutes? For example, a kind of ChatGPT interface to Polyworks capabilities.
It's a good question.
Yeah.
It of course, right now it would be completely out of the question, let's say, to just have something as simple as ChatGPT, where you say, can you make an FAI report of this part? Simply because at first, okay, putting the CAD in, well, you need to identify that CAD model, that part number. So you need to have that information. The rest is not so far-fetched, though, because once you have the model, if the measurement plan that was established correctly in a company for a particular part model, if, for example, all the geometries or features and controls that are supposed to be measured with the tolerances are all embedded inside that CAD file, then we're not so far from this. And we do have a solution that's called our Polyworks PMI plus loop solution, which is used in combination. It's an add-in for a CAD software, where a designer with the team of engineer, because generally speaking, the designers would not be the ones deciding on the measurement plan, but you could predefine in there the datum features for an alignment, the geometries, the controls, the tolerances, and that can all be brought inside Polyworks Inspector along with the CAD file when you read it. And from there, we do already have automated tools to generate the first article inspections. So for those of you who might have an interest, don't hesitate to contact our tech support team. These are things that we can orient you with. But yeah, so like I said, it wouldn't be something that would be voice activated, but there are ways of making a piece template ready to receive 3D measurement data in very quickly if the organization put all that information in the 3D CAD model.
Hey, thanks, Jean. I guess quite specific, that question. So I'll just move on to this next one from the audience, from a participant in the audience. This person's called Otis Burnside. Thanks, Otis, for your question. They would like to know how can engineering education at university level be improved to use modern measurement technology because of the rapid changes in technologies? Should such training be company or software specific? Well, you've got the university connection, or Tom, you quite connected to the industry through BINT as well, aren't you? And so I don't know who wants to go first on this.
Do you want me to start, and then Tom will? I'm sure Tom will chip in. I think one of the key things with university engineering education, is particularly in metrology, is the understanding of the principles of metrology. When you get back to it, the fundamentals of metrology in alignment and setup and what you need to do in order to measure a part will always be very similar to what they've always been. So it's about, getting models set up, datums, and in some ways the engineers that we receive have had you don't really want to learn the software until you understand the basic principles of alignment and the way that things should be measured. Because once you've learned that, then realistically, the software and the tools that are out there are almost like a toolbox you can then go into to find the right tool to do the job that you need, and you have to learn that software. So in my opinion, rather than focusing necessarily on one or two specific processes, what the education needs to do, and what we try and do when we're teaching people, even at the AMRC in measurement, is looking at those principles of fundamental alignment, the repeatability of measurement, the understanding of alignment and how it works, and then how you take those measurement points and what they're doing for you. Because in industry, some of the software can be quite heavily misused once you get into best fit measurement and all of the other tools that people use. Without that fundamental understanding, you can still make some pretty significant errors, no matter how accurate equipment or how powerful your software. So in my view, it's that basic understanding of what does metrology require is key in education. And then the tools become the tools you use to take over that task. I don't know, Tom, if you've got a view on that. I don't know if that's similar or...
It's a lot of the processes all until recently would have been in grandfathered systems where you learn from your peer or you learn from the OEM who supplies the equipment, and not in a very methodical, well laid out proceduralized process. We are trying to improve that. We're trying to look at elevating the level of person who's using quite sophisticated equipment, and also to understand, what goes wrong. We within some of our local business unit here, we would run, like a gauge R&R, where we do a repeatability and reliability exercise. We give the component, use the same measurement tool to a number of different operators and get them to run through that process to fully understand what they're actually measuring and to show the drift with time or between different operators, even using the same piece of equipment. But because we're starting to use more automated equipment, we're having to look at the challenges of improving the education of the people who are using the equipment, trying to bring in, and we have an issue with age, in regard to people who are of a certain age are not as quick with uptake of technology. That's not right across the board, but younger people tend to have grown up with technology or tend to be quite capable with technology and tend to be quicker at taking on new techniques or some automation of processes, etc. And do we need to teach mechatronics or something as part of a college or degree course? I do believe it should be part of even apprentices coming in to organizations for manufacturing. There should be some mechatronics and automation being involved in their education at an early stage.
Yeah. One other thing that is rapidly changing, I think, or maybe the most rapidly changing, goes back to the data that we were talking about. So, for instance, our measurement tools will produce 4 million data points at a push of a button across a surface, and then those 4 million data points, the various analyses you can do on them. If we just look at the 3D S parameters that are ISO parameters on surfaces, there's 50 some different parameters, right? And so there's just so much data now that teaching people how to interpret it, how to bring it in, how to determine what's relevant or not, and how to differentiate correlation versus causation, and how to properly archive it so that, again, you can go back if later on you find your process has been out of control or something changed, and you go back and say, hey, this thing that I was never controlling for but logging, that's the thing that actually changed when my parts went from bad to good. Those types of operations, I think, are new as we move more into quantization and digitization and getting feedback from machine tools, and their health as well as the surfaces themselves. There's just so much out there that you have to wade through, and you can go down rabbit holes that are really bad, or rapidly come to astoundingly good conclusions that let you improve your processes. But at this point, it's almost a bit of an art to properly manipulating and interpreting data, and I think that's a big component I see going on more at the education at the university level, is teaching people how to handle these massive amounts of data and these extremely complex production processes.
This is where software also has a role to play in exposing that to the operator, to the user, but also guiding him. This is one way we've been making a lot of progress in the last few years. For example, just to complement what Erik was saying regarding the data. I mean, yes, there are scanners that can provide a huge amount of points, but have you used that scanner in the best possible way? A very simplistic thing that we've thought in the past, that nowadays the software doesn't have to or that we don't have to teach anymore because the software takes over, is when you hold a scanner above a surface, ideally you want to be as square to that surface as you can. It's just an optical principle that makes the data, if you want, a bit more noisy if you're at an angle. So the software detects that and guides you using color coded. This is what we call the real-time quality meshing. So as you're scanning, you see kind of a quality factor being shown as a color on the surface you're acquiring. Of course, this only works if you're doing interactive scanning. When you have an automated system, you have better control over that. But in the past, we used to have to teach people how to do this, and they had to be, self-regulating themselves and making sure they do it right. Nowadays, the software exposes you to, hey, maybe you haven't scanned that in an optimal way.
Yeah, thanks for that. Surprisingly, we're almost well, we're 40 minutes gone already. So if anyone has got any more questions, then please do. But I wanted to lead the discussion background. Actually, it was something that Tom mentioned, and we're on the topic of onto the topic of automation as a way. I guess I'm looking at automation in terms of it can help in terms of software and maybe in terms of robotics as well. I mean, how is that helping manufacturers meet targets and or people doing QI? I mean, how is that introduced? Tom, do you use automation in your quality inspection?
We do. We obviously use quite a lot of some obviously manual manipulations to some extent. We use firearms. We use fully bespoke CMM measurement systems that are gantry based or tower based or even some robotic based systems as well. We also do some dynamic measurement using robotic systems. We're allowed, some people say the accuracy isn't what you want, but we're using it to move the end effector, and we're using laser 3-point projection to actually capture the data. So we're just really using the robot like a person, but doing it much more quickly and to a much better tolerance and can reach over large areas. So yes, it's still some of the issues that we have. We capture huge amounts of data, because we're covering large areas. And within that data is all the key characteristic points that we wish to measure, whether it's an aperture, whether it's a hole, whether it's a fit up joint or whatever. And we are struggling sometimes to get, we use software to make it simpler to look at the key characteristics only, but still understand that the rest of the component meets the CATIA requirements or the measurement requirements, but ignoring it and moving to the key characteristics where we've joint up and that sort of thing. So automation is really, really important. I don't think we've fully cracked it. I think there's still some work to do there. And it's really understanding what the best process is and where you put a fully automated measurement system in, and what part and what stage of the process do you put it in. Technically, it's too late when you've done everything at the end. If you put a full measurement system in at the end of your process, it's valuable because you're not sending non-conforming part out, but the capture mechanism should have been earlier in the process.
Sounds like it has to be very judicious, the way it's introduced into the environment, right? The manufacturing. Yeah. Okay.
Yeah. And we see a lot of people really targeting, there are really inefficient parts of the process. So one of the things we've seen is, people that are using replication techniques and then cross-sectioning and optical comparators to do that process for looking at a micro geometry can take a half hour or more per point, right? And so recently we've actually gotten adoption of systems in automation where they just want to measure those micro geometries, radii, chamfers, edges, and things like that directly. And so in some cases, in one instance, I know the inspection process went from more than a week and a half to under 5 minutes, just at 160 callouts. just from removing all those different manual steps of inspection that had been involved. And so, there's pain points people target, and but you see that a lot. 5 years ago when we talked to a lot of people about automated inspection, yeah, people were using CMMs and not much else. Now you can't, even in the MRO world, you see lots of automated inspection going on, even though some of what they look at is very different from part to part in terms of corrosion or wear and things like that. So I think one, the labor shortage, people let too many people go during COVID in aviation and they're unable to replace that. And two, just the drive for efficiencies are really pushing a lot more automation a lot faster than I would have expected had you asked me, 3 years ago, where would automation be in the aviation inspection business?
Rob, I'd like to bring you in here. You must work with automation and your background in composites as well. And inspecting composites. Can you talk around that a little bit? Is that relevant?
Yeah, generally speaking, if you look traditionally at the composite inspection, it would have been someone manually laying up a part and then each ply being looked at in the way that Tom was describing earlier. More recently, we've started to look at much larger structures, and as I say, we're building a facility to do very, very large structures. And realistically, you're not going to be able to inspect those without automation. And in a fully automated environment, you don't want to have to bring people in to confirm what you've already seen. So the automation of these processes, in particular the sort of optical processor or edge scanning of plies to understand a ply position, for example. So you've got two challenges. You've got the actual positioning of a black on black ply, which is quite hard to see at the best of times. And when you automate it, you've then got to scan its edge and decide whether or not it's positioned correctly and oriented correctly. And it's still quite a significant challenge. There are systems that will claim to do it, but there's still not really 100% in my experience, 100% reliable. One argument says, I mentioned earlier about large parts being laid up. An automated process that can't necessarily identify the fault, but identifies an area it's not comfortable with, is still much better than a process that doesn't look at anything. So if I talked about this very large layup that I was talking about before, where we had 3/4 of an hour to lay it up and an hour and a half to inspect it, all you really want then is to bring and that hour and a half inspection was because they would only trust a person to do it. But if you automated that to the point where instead of the automation trying to say, this is definitely what's wrong here, it just says, I'm not comfortable with this area. Most NDT is looking at good structure. At the end of the day, our processes are well controlled. And whenever you do NDT, most of the time, whether it be visual inspection or other types of NDT, you're looking at good structure. So the first thing to do is to try and focus in on the areas that aren't good and remove 3/4 of the rest of the time, if you like, because the automation is all about time and consistency. So our challenge now is to try and understand how well we can automate the processes, and then it's about trust. And I think that's in the aerospace industry in particular, that's the area where there's still quite a bit of work to do to demonstrate the reliability, despite the fact we all know that the software does a great job, the instruments that are measuring do a great job. It's that assessment of the result and trusting the systems to make those assessments is probably the key challenge at the moment, I think. Tom,
I agree. What we want, the value-added inspection is areas that are not conforming. That's where we need to be looking at. The areas of inspection that the parts conform consistently and can be quickly measured. That can be very, very easily automated. It's where you have problem areas, or the system or the software can recognize there's a problem and it flags the problem. If it needs a human integration at that time, then it flags it for that review to be done. But it does speed up the process greatly.
This is where AI and assessment of data and reliable data becomes critical in if you like, beginning to be more predictive in that rather than reacting to the and that's where you can narrow down the real key areas that are all that we believe are giving us problems. And on that, you need reliable hardware and software to give you data you trust, then, isn't it? And so, yeah, but that's well, that's my view on it anyway.
Yeah. Okay. Thanks, guys. Yeah. Just 10 minutes. If there's any last questions from anyone watching, now's the time. Absolutely, get them across. But I'd just like to bring things back slightly and in the wider kind of supply chain and the role that that inspection plays in it. I mean, ultimately, there's these parts are going to customers, and I mean, where's that are making aircraft? What kind of pressures are coming from those customers? In the supply chain. I mean, and how are you really responding to them? How do the tools that we have? What are the most useful things that they can do? I mean, presumably, when I'm talking about the pressure, I'm talking about doing more with less, doing everything faster, right? Is that the kind of pressures we're talking about? Tom, I'm probably directing this at you, to be honest.
Yeah. Currently, the supply chain is difficult, and it's simply down to probably not being able to deliver on time because of shortages, and this is worldwide, and it's definitely across all the major prime aerospace manufacturers, but it's in the rest of the supply base as well. Even nuts, bolts, they are all difficult to actually get on time. The likes of carbon fiber, resins, it's all been very, very difficult to get things on time, or there's shortages, and we're waiting for factories. There's times when we have to deliver components to the rest of our sites across the world with some components short on them that have to be installed at a later date. Now that actually can compromise your inspection plans or metrology plans, because you can only give a part plan to the next stage or the next manufacturing zone or the next assembly zone, because you haven't installed the part that there's a shortage in. And if we push back into the supply chain, they're pushing back right back to the raw materials as it's coming potentially out of the ground from metallics, or as it's being woven. They're having to increase or push every aspect of their supply chain to try and meet our supply chain. And a lot of inspection processes have been put in to try and make sure that we have reliable, consistent product. But that can slow down the supply chain as well, and it can make it struggle. And sometimes you can't deliver a fully conforming product to the next stage of your process simply because you have a shortage or you can't measure it appropriately. And that is a big issue right now, and that's a sort of a knock-on effect from the COVID issues and factories shutting down across the world. We still have not got back up to the production levels that we were at. We've lost people in the industry. They'll want to come back into the industry. People have retired out. We're not getting the replacements coming back, through into the industry anymore. They're looking at different types of jobs, different types of roles. They're looking at hybrid working. It's all
Yeah.
It's slightly different than the question you have asked, but it's.
I'm just finding it makes me think. I mean, what role here does kind of either tools that are out there already, technology that's out there already on the market, or stuff that perhaps Rob's and his colleagues at the AMRC are working on? Like, are we looking at ways to alleviate these kind of pressures?
If you get away from the supply chain issues, then in the end, the way that you inspect won't necessarily hold you up. In my environment, we're looking at what we do next, if you like. So, I mean, I'm looking at techniques we're going to be using in 10 years' time on aeroplanes. So,
Sure.
But in that regard, when you get to large composite structures, at the moment, rate is the problem. We can produce very large structures for aircraft at fairly low rates. But if you start getting up to single aisle rates, then the technologies that not only produce the parts, but inspect and validate the parts are all going to have to be upgraded and be working at a rate that at the moment would seem almost impossible. So any hiccup in that is going to affect supply. And so our challenge now is to try and understand all of the challenges that Tom's described, and then multiply them by a rate that may go up by sixfold. And I think that's my future challenge, if you like, in terms of this sort of lower TRL research area, is trying hard to integrate the systems in a way where the speed increase required in production doesn't mean that we're held up by inspection.
Yeah.
We still have to do it, but we just have to integrate it in a way which means we can meet the rates.
Right. Yeah.
Does that make sense?
Yeah, sure. No, thanks, Rob. I like that. I like that some of you that we're thinking hard. It looks like everyone's starting to think hard, so, which is great. I just had a question in here from a person called Matthew Davis, and it looks like one that's going to make everyone think hard. Erik, he mentions you here. A few of you, thinking of Erik, he writes, has mentioned the need for removing the bottleneck of measurement labs by moving inspection to the shop floor. Naturally, the results will be different due to the equipment used in the environment where the measurement is taken place, etc. How are these variations accounted for? I guess is his question.
Yeah, so that is a challenge sometimes, and it's a challenge both ways. There are compromises that happen by moving metrology to the shop floor. For instance, our one handheld gauge, it has micrometers of resolution, whereas some of the 3D microscopes in the lab have nanometers of resolution. Now, a lot of times in aerospace, the part spec doesn't get much more than 1,000th of an inch or 25 microns. So having 1 or 2 micron resolution is fine, but it's still going to give a different level. And so you do have to do correlation studies. There has to be validation, of the methodology. And then the other big challenge is really just ease of use and getting that feedback. So for instance, we don't rely on an operator to know when a part is in focus. We actually color the live video green when the measurement is ready to go. And so green means go, you hit the button, and they're not making, judgment calls based on 20 years of using a microscope or because they were trained on it at university or something like that. So, but the real key is, understanding what specifications are important, doing correlative measurements, doing some gauge studies, making sure even your gauge study is properly set up so that you have enough part variation to be meaningful and things like that. And then accounting for, the operational differences, that it's a different level of operator and all that.
Okay, sounds like some good advice there. Does anyone want to answer that question, or is Erik done the comprehensive job on it?
I think underpinning all of this in the end is that when we design parts, we have to make sure that we apply the right tolerances in the right places, and we don't just blanket increase the tolerances because we can measure them. And I think there's a lot of importance needs to be given to, when you're looking at design for manufacturing, all of these other things, is ensuring that when we really need to check a tight tolerance, we check it, but we don't then just blanket apply it across product as a default, if you like. And so it goes right. I mean, these costs and these potential failures are built in right at the point when you design a part. It's very important that if you're going to automate it and do that sort of inspection on the shop, you do the inspection that's really needed and not cover it with inspection that actually isn't helping you to produce a better part. I think that's key. I think it's really important to understand.
Yeah, some engineers do get aggressive on, well, machining got better, so I'm just going to tolerance everything better.
Yeah, exactly.
I think our issue is that the tolerance should be good enough for the design requirements.
Exactly.
The measurement process should meet that design requirement, but also be capable of highlighting the drift. And if they want to measure that drift very, very accurately, then that's appropriate. But it's not measuring the tolerance to the extreme level of accuracy, but it's measuring process drift to a very good accuracy.
So you really, looking at capability.
Yep. Right. Well, we're almost at time, guys. Thanks, and it's a testament to how interesting this all is that the hours zoomed past. But I would just like to finish on one final question and ask you all to speculate slightly. I know engineers often don't like speculating and guessing about stuff, but it can be a fun process. So, I mean, what do you think? How do you think inspection processes and technologies are going to change in the kind of near future, 5 to 10 years time? Do you think that what inspection processes and technologies do you think are going to be used more? Where manufacturers, aerospace manufacturers, focusing in on? What's going to be important? Jean, do you want to go first? I'm picking on you.
Yeah.
Summing up.
To me, what I foresee as being probably the future is not that much huge improvements, because there are already tons of technologies out there that are suited for the different tolerance level or different application. I think what's the future is really an increase in the demand for inspection results and 3D measurement data, because the availability of those results will have made their proofs into how well you can take engineering decisions, do root cause analysis, and improve your whole manufacturing process simply by having data as your facts. So I believe that this is the near future that we are getting to.
Great. Rob, do you want to go next?
Yeah, not really anything to add to what we've been saying all along. I think in the near future, it's going to be applying these new technologies in a measured way. Sorry for the pun, didn't mean to do that, but at the same time, being much better at using the data to be able to predict what we should be doing in the future with regards to measurement. So I think the one thing is we have fixed measurement plans at the moment, but as we use AI and predictive tools, we will be able to adapt what we do to measure the things that really matter over time. And in some cases, the regulation we're bound by in aerospace means that someone's got to have a think about how we go about that, in fairness, so that the processes can adapt to what they've been capable of over an extended period of time. So I think there's quite a bit of work to do there.
Mm-hmm. Erik, your turn.
Yeah, I also think we're going to see a greater push for not even just shop floor or nearline measurements, but right with the process equipment. So as manufacturing goes to more additive manufacturing, to more automation, where you're measuring it as you're machining it, you're measuring it as you're laying down the next layer or whatever it is, and just getting that feedback instantaneously. That's always the desire, right? And there's a lot of challenges there with cleanliness and all these other things. But I think there's going to be a more and more push there. And then, yeah, as Jean-Sébastien said, data analysis and interpretation, so that you get that rapid feedback.
Thanks, Erik. Tom, you get the honour or the curse of going last, I'm afraid.
No, it's exactly what the guy said there, and I think we're going to end up. We'll be in a non-contact world where we'll be doing, a non-contact metrology approach, and in line with how we manufacture components. That's what we need to get to.
Okay. All right. Great. Well, I think that's a great place to finish. So I'd like to thank the sponsors, InnovMetric and 4D Technology again. Thank you. I'd like to thank the speakers here all for your participation and your focus in dealing with the questions and speculating when I've asked you to. And it's been a fun discussion. I hope you guys have enjoyed it too. And finally, I'd like to thank the audience for your attention over the last hour and your participation where you did participate. This recording will be made available for on demand. Everyone will receive an email shortly after the event to watch again if they want to. So thank you. Yeah, it's been a pleasure. Wherever you are in the world watching, I hope you have a great day. Cheers.
Bye, everyone.
Thank you.
Thank you.
Bye, everyone.